we're interested in looking at polynomials, and we're going to kind of dive into what our textbook calls that's looking at these kind of specific details that will tell us information about the polynomial we're looking at. So the first detail we're going to look at are vertical horizontal intercepts. Previous algebra classes, we often call those y-intercepts. Those are the intercepts that occur when the graph crosses the vertical axis. So here, let me just draw a little picture over here. So right here, boop, that is the vertical intercept. Okay. Value occurs when our x, or whatever the horizontal axis is, when that is 0. So here for ease, I'm going to go ahead and refer to this as x and y, just so we have labels, traditional. So this is going to actually cross the y-axis and x equals 0. Okay, so horizontal intercepts, that's when the graph crosses the horizontal axis. So in our picture then, that would be right there. All right, so that occurs when y equals 0. Now it does get a little bit more complicated in the sense that, oops, sorry, when we're starting to talk about function notations and polynomials, what we'll really be looking at for vertical intercepts, this is kind of nice, we'll basically be plugging in 0 into our function, whatever that is. And whatever we get out is going to be our intercept. Now, since we're talking about polynomials, and you might remember from earlier here, let me go ahead and do it in a different color, that a polynomial can be written in this form, a to the n, x to the n, a to the n minus 1, x to the n minus 1, and it keeps doing that until we get to 2, 1, and 0. Okay, so that's the basic form for a polynomial. So if I plug in 0 for x, basically every term that has an x in it is going to go away, right? That's got an x, that's got an x, x. All the terms in the dot, dot, dot are going to have x's until we get to the very last term, which doesn't have an x. Therefore, this is actually going to happen at a sub 0. So this point here is going to occur based on this constant number at the end of the polynomial. That's not a coincidence. Another way of writing it, by the way, is in ordered pair notation, 0, comma, a sub 0. Okay, but when we're looking at horizontal intercepts, not as clean. With a horizontal intercept, what we're instead doing is taking f of x and setting it equal to 0, which basically means in order to solve that, we're going to have to look at different methods that we can use to solve something where it equals 0. We'll talk about that in more depth. But there is a special name for horizontal intercepts. So these are also known as, so I'll put AKA, also known as 0 or roots of a function. So those are two other words we use. Other than horizontal intercepts, they all three represent the same basic idea. These points where the graph crosses the x axis. So the technique for finding horizontal intercepts is going to be slightly complicated. I'll go ahead and kind of give you some spoiler alerts. We're going to possibly do some factoring, maybe quadratic formula, and some other fun things like that. But we'll get to that as we kind of continue developing our understanding of polynomials. The last major thing with a polynomial that we're interested in is what's called a turning point. Now, a turning point is the idea that the graph is like changing a direction from increasing to decreasing. from increasing to decreasing. So a turning point on the graph is clearly where it's changing. And because I kind of muddled that graph here, let me do a different graph here. I'll even make it a little bit more exciting. Let's see, how about something like this? Wow, so exciting. Okay, so on this actually has 3 different turning points. It turns right here, right? It goes from decreasing to increasing, and it turns right here, goes from increasing to decreasing, and it turns right here again, goes from decreasing to increasing. So those 3 would represent turning points. We'll get into that too a little bit more detailed in a little while. Let's look at an example and kind of dive into the vertical and horizontal intercepts, which is something you probably have worked with before. So given this polynomial, which is actually written in factored form, how nice, let's find the vertical and horizontal intercepts. So starting with the vertical intercepts. So that means we're going to find f of 0. So I'm going to plug in 0 for x. Now, because this is in factored form, I don't see it in the form where I already know what the last term is. It's not all multiplied out. Oh, sorry. Everywhere I see x, I'm going to put a 0. And I didn't do that. So I'll actually figure this out really quick. That's going to come out to -2 times 1, which is -2 times 4, which is +8. So there we go. The vertical intercept is 0, 8. Or f of 0 equals 8. But I believe they favor ordered pairs in the homework. I can't quite remember. They might do both. Okay, horizontal intercepts. That's when we're going to take the function and actually set it equal to 0. So I'm going to take x minus 2 times x plus 1 times x minus 4 and set it equal to 0. And we know because this is already factored, we can solve this by setting each factor equal to 0. So x minus 2 equals 0, x plus 1 equals 0, and x minus 4 equals 0. So in this case, adding the 2, x is just going to be a 2. There's 1. Minusing 1, that's going to give me -1. I'm not going to show the work. I'm just going to kind of skip it. That's going to give me 4. Okay, so there we go. We actually have 3 horizontal intercepts, and they occur at 2, 0, -1, 0, and 4, 0. So in this case, all of the y values are 0. Right, which makes sense. That's what f of x equaling 0 means. That means I'm taking y and setting it equal to 0. All right, now let's kind of talk a little bit more about turning points and intercepts. So really quick, a polynomial of degree n, highest degree is n, so maybe it's 3. It will have at most n horizontal intercepts. So in my example, if I'm talking about like f of x equaling x cubed, and that happens to be the highest one, okay, it would have at most 3 horizontal intercepts, okay? An odd degree polynomial will always have at least 1 intercept. So there are actually examples of even polynomials that don't have intercepts, and we'll talk about that in the next section. And it will have at most n minus 1 turning points. So when it actually turns that pattern of turning, it's 1 degree less. So a polynomial that here, let me like actually make it interesting, plus 8x squared minus 100. I don't know. It's a terrible looking polynomial. Who cares? In this example, this would have 3 or at most 3 horizontal intercepts and at most 2 turning points, which makes sense because it's an odd degree. So since it's going to resemble x cubed, that means it's going to kind of follow this basic pattern, right? Like where it does this. Okay. But it might look something more like this, where it actually does some turning, right? And in this case, 1, 2 places at most. It could potentially have no turning points. Maybe it resembles more like x cubed, where it does this, kind of has like a funny flat point, but that has no turning points, all right? But no matter what, it's going to have at least, it'll have at most 3 horizontal intercepts. So here, if I draw the graph, boop, or the axis, there it is. There would be, I tried to do it in green and it switched to blue on me because it wasn't ready for me to actually draw that. And of course it all disappeared. Wow, what a dork. Let's try this again. There we go. And I think I did somewhere like that. Okay, close enough. These would be the horizontal intercepts. And as you can see in this particular example, I managed to get 3 of them. Doesn't have to be. I could have shifted the x-axis, right? The x-axis could be down here, and then there's only 1, but it has at least 1 because this thing is going to always go down. So no matter how far I lower the x-axis or raise the x-axis, it's going to cross the x-axis. Okay. So that kind of plays out. All right. So let's actually look at an example. What can we conclude about the polynomial shown here? Okay, wow, lots of things we can conclude. I see some horizontal intercepts, a vertical intercept. I see some turning points. So let's kind of zero in on that. And let's talk about the long run behavior. So I notice that as x goes to negative infinity and positive infinity, that f of x is going to positive infinity. So that probably means that we're looking at an even polynomial. It does mean that we're looking at an even polynomial. So I'm sorry, a polynomial of even degree. So a squared, a fourth, a sixth, something like that, okay? Or eighth. Okay, that's first. Now, actually, it's got how many turning points? Let's start by counting how many turning points and how many intercepts. So let's see, we have 2 horizontal intercepts. So minimally, this thing has got to be degree 2. Now let's count how many turning points it has. 1, 2, 3 turning points. Okay, now that actually tells me something. That tells me that minimally, this has to be degree 4. Because the characteristic is it has at most n-1 turning points. It's always 1 less than the degree. So this has to be at least degree 4, could be degree 6, could be degree 8, okay? But at least it's degree 4. That much I know. So that's really what my big conclusion is at this point, is I would say minimally this polynomial is degree 4. Honestly, I'm basing that on the turning points, but the other information really secures that. The fact that I knew it's going to be an even degree. Oops, I'm supposed to switch the highlighter there. And of course, I'm going to end up erasing more than I wanted. Yep, of course. There we go. Boop. I wanted it to be even degree. I know that. And then the 2 horizontal intercepts. So we know that the intercepts, it's at least that the degree of it, but it doesn't have to be. So having 2 horizontal intercepts, there's nothing wrong with that. That's reasonable for an even degree polynomial. So what you'll see on the homework is kind of looking at those types of things and figuring out at least the minimum degrees based on that information.